our very own Professor Larry Widrow to give our colloquium. So thank you very much for that. If you don't know Larry, which hopefully everyone here does know Larry very well, he got his PhD at the University of Chicago before continuing to do postdocs at the Harvard-Smithsonian Center for Astrophysics and then at CETA, not too far away, before coming to Queens. He has had a variety of research interests in his past, starting with more of an astroparticle physics and moving into galaxy dynamics, the latter of which he is going to talk about today. So thank you very much for giving our colloquium, and we look forward to your talk.
Great. Thank you. Mic's on. Thank you, Sarah. Let me begin by mentioning that the title for this talk is actually borrowed from a workshop that I attended at the lovely Kavli Institute for Theoretical Physics at UC Santa Barbara during my sabbatical in the year prior to the pandemic. And so this was meant to be a post-sabbatical colloquium. It was canceled twice. The first was so that I could take a citizenship oath. So this is my first in-person talk as a Canadian citizen after 30 years here. And the second was because of this nasty bug, but it's great that we're all here now and we're past the pandemic and we can all, that's a joke. Right? Wondering earlier this week if this was going to be postponed again. So let me give a quick overview. So I'm going to begin by saying something about equilibrium models for disk galaxies such as the Milky Way. And then we'll look at some of the things that you could do with equilibrium models, and in particular, a calculation known as the Oort problem that allows one to infer something about the local gravitational field of the galaxy and the local dark matter density. And this is really something that complements rotation curves, which we often hear about in discussions of dark matter. The main part of the middle part of the talk will describe disequilibrium in the Milky Way, the ways in which the Milky Way galaxy is not an equilibrium system. And then we'll come back and talk about something known as phase spirals, which you'll learn quite a bit about in this talk, and revisit the Oort problem. So let's first get ourselves oriented in the Milky Way. The Milky Way is the closest edge-on galaxy to the sun. We're viewing it through the disk, sitting very close to the midplane of the galaxy. We sit about 25,000 light years from the center of the galaxy, or about 8 kiloparsecs. And that center is dominated by galactic bulge and bar, which account for about 10 or 20% yes. Yes, that's an excellent idea. Thank you, Stefan. Better? Too much? OK, is that all right? Yeah. OK, thanks. And so most of the mass in the disk is actually in this stellar disk. And so let's take a bit more of a look at that. If we look at the stellar disk and azimuthally average the mass in the disk and also integrate through the thickness of the disk, then we find that the surface density, the mass per unit area in the disk, roughly falls off exponentially with a scale length of about 3 kiloparsecs. And so we're sitting here about 2 or 3 disk scale lengths from the center of the galaxy. The stellar mass of the disk is about 50 billion solar masses, and that's roughly 50 or 100 billion stars. And the sun has an orbital period around the galactic center of about 200 million years and a rotation speed of about 200 kilometers per second. So what do we mean by a model for the stellar? Defined in terms of 2 mathematical functions, one of which a distribution function, which describes the density of stars, not just in terms of position, but also in terms of velocity, a 6-dimensional phase space density, and also the gravitational potential, which tells the stars how to move. Stars in the disk are assumed to be collisionless. In other words, we're doing mean field dynamics. We're ignoring star-star encounters, which are exceedingly rare in the disk of the galaxy. On the other hand, if we were doing globular cluster physics or open star cluster physics, we would have to think about how individual stars scatter gravitationally off of each other in the disk of the galaxy that turns out to be not necessary. So the potential and the distribution function are connected through Poissons equation, and also the dynamical equation known as the collisionless Boltzmann equation. For an equilibrium model, which is our starting point for this talk, the distribution function and the potential are both time independent. And if you think about it for a moment, you realize that to build an equilibrium model, except for some highly contrived cases, the galaxy, such a model should have axisymmetry, symmetry about the spin axis of the disk, and also symmetry about the midplane. It's very hard to construct an equilibrium model that doesn't have those symmetries. So a model for the disk is built out of individual orbits, and here's a picture that I took from some astronomy textbook, and it shows the difference between the orbits of stars in the disk, which are nearly circular orbits, and the orbits in the inner bulge, which are randomly distributed orbits, and the orbits in the stellar halo, which are also random orbits. And so the disk stars, their orbits are characterized by being on nearly circular orbits, all moving in the same direction about the galactic center. Stellar orbits can best be thought of as a superposition of three oscillatory types of motion. So the first is the most basic. It's the one we all learned about in our early courses. It's the circular motion about the galactic center. We apply Newton's second law, and that tells us the speed of an orbit as a function of radius. And essentially, that speed goes as the mass interior to the orbit divided by r to the 1/2 power, just basic first-year physics. It's often useful to talk about the angular frequency of these orbits, so just take v over r, and you find that this frequency is proportional to the mean density inside your orbit, which is a result that you could get from dimensional analysis. If you think of Newton's constant g and density, then you put those together to get a frequency that's just g rho to the 1/2. Galactic rotation curves are intermediate between two special cases of the potential, the two cases that we learn about in our early physics courses. So one is the Kepler potential, where we put all of the mass at the center. In that case, the velocity falls as r to the minus 1/2. The frequency falls as r to the minus 3/2. That's one of Kepler's laws. And then the other example is the harmonic potential, in which we have constant density. In that case, the velocity increases linearly, so it's essentially solid body rotation, and all particles orbit the center at the same frequency. And the galactic rotation curve is essentially intermediate between those two. So that's a good benchmark to think about when thinking about the orbits of stars. So we can now build the first ingredient for our equilibrium model. We have stars which we can define their orbits in terms of an angular momentum, which is just the angular frequency times the radius squared. And how we populate those orbits determines the surface density. And so if we want a particular density as a function of radius, then we just have to figure out how to populate the orbits. In other words, that surface density is telling us something about the angular momentum distribution of the stars in the disk. Of course, stars do not move on perfect circular orbits. In the Kepler problem, stars move on ellipses with the center of the potential at one of the foci. Notice that each of these stars is making one radial oscillation, that is going from maximum to maximum, in the same period as it makes one orbit around the center of the galaxy. And so we call that radial oscillation frequency kappa, and in this case, kappa equals omega. So that's one of our two sort of benchmarks. And the other is the case of constant density. In that case, stars move on elliptical orbits with the center of the potential at the center of the galaxy. In this case, notice that, first of all, the frequency is the same for all of these stars, and they're making two radial oscillations for every one trip around the galactic center. And so in this case, kappa is 2 omega. And so if galactic potentials are intermediate between these two, then we have a kappa that's between omega and 2 omega. And in this case, stars make elliptical orbits, but the major axis of the ellipse is precessing with time. In other words, these stars are tracing out these beautiful rosette patterns in their orbits. One of the things to realize about these rosette orbits is that if you take two stars, one on a circular orbit and the other on a rosette orbit, and they have exactly the same angular momentum, the circular orbit wins, and this star on the rosette orbit actually starts to lag behind. You can see that most clearly if you go to the rotating frame of the circular orbit. In this case, that star on the rosette pattern just makes this curly Q pattern, lagging behind the star on circular orbits, and so drifting behind the rotation that you would have if you were on a perfectly circular orbit. That's something known as asymmetric drift. And if this curly Q pattern seems reminiscent of the old Ptolemaic model, the epicycle model of the solar system, that's good because astronomers in galactic dynamics use epicycle and epicycle approximation to describe this motion and this way of thinking about these orbits. And so now we have the second ingredient of our equilibrium model. We have stars of a given angular momentum, which could follow a perfectly circular orbit. But then there are stars with a little bit more energy, but the same angular momentum, and they're oscillating in radius and in radial velocity and in azimuthal velocity about the path of a circular orbit. And so we can distribute, in building our model, we can distribute stars with these different energies relative to the energy of circular motion, and that will tell us something about the distribution of stars in the VR V phi plane. Okay, so now we have two ingredients of our model for the disk. So the final component is the motion in the vertical direction. If we think of stars very close to the midplane of the galaxy, then we can treat the vertical motion, that is the motion in and out of the plane of the disk, as essentially a separate motion, a separate type of oscillatory motion. And so now we can consider the distribution of stars near the sun relative to the midplane. So z is the distance from the midplane of the galaxy. Vz is the velocity perpendicular to the plane of the galaxy. And here's a z-vz plane, which we're going to be seeing a lot of in this talk. And so here's a z-vz plane of an equilibrium distribution. Stars would orbit in the clockwise direction in the z-vz plane. The thickness of the disk is defined by how spread out this distribution is in z. The vertical velocity dispersion is defined by how spread out they are in Vz. And so for this final ingredient, we can populate the orbits in terms of their vertical oscillation in terms of this energy associated with these vertical motions. That is the kinetic energy in the vertical direction and the kinetic energy in the vertical direction and the position, the gravitational potential energy in the vertical direction. And so here's the way we construct our equilibrium model. We essentially multiply these different distributions which describe how stars are distributed in angular momentum. That determines the surface density profile. How they're distributed in energy relative to circular energy at a fixed angular momentum. That determines the distribution in radial velocity and azimuthal velocity. And how they're distributed in vertical energy, which determines the thickness of the disk and the velocity dispersion of the disk in the direction perpendicular to the plane. We multiply all these together, and basically this is our equilibrium model of the galaxy. One of the popular examples for finding an equilibrium model is something called a quasi-isothermal distribution, and many people have been working on this for some time. It serves as a useful template for interpreting observations and also as initial conditions for n-body experiments. Quasi-isothermal because you essentially assume a Maxwellian or isothermal type distribution for the vertical energy and this energy in the plane that determines the radial oscillations, and as well, some function which determines the surface density. So what can you do with equilibrium models? Well, equilibrium models allow us to interpret things like the rotation curve of the galaxy. For example, if I generate one of these equilibrium models and I plot the azimuthal velocity of all the stars in the model, I get this cloud of blue points, so it's got some velocity dispersion to it. But if I average at every radius, I get this red curve, which gives us the mean velocity of the stars going around the galactic center. On the other hand, since I built the model, I know what the gravitational potential is, and I get that black curve. And the difference between these two is that asymmetric drift effect that we talked about earlier, the fact that stars on these rosette orbits are lagging behind the stars on circular orbits at the same angular momentum. And so when interpreting a rotation curve, one has to be careful to take into account things like asymmetric drift. So galactic rotation curves have, of course, provided compelling evidence for dark matter. We've seen rotation curves in Colloquium in this department an innumerable number of times. Here's a map of M33, one of the closest galaxies to the Milky Way, a companion of M31, Andromeda, in fact. And here's a map showing the line of sight velocity of this galaxy. And so parts of the galaxy are receding from us, parts of it are moving towards us. It's telling us that the galaxy is rotating. And then from this, one can infer, taking a slice, say, down the major axis of the galaxy in projection, one can infer the galactic rotation curve. M33 has this rising rotation curve, but most galaxies, the rotation curve is pretty flat. And it's the difference between the rotation curve and what you expect from all the visible stuff in the galaxy that leads us to postulate, to infer that galaxies are surrounded by dark matter halos. So we can play the same game in the solar neighborhood. Essentially, we can look at stars and think about their vertical motion, and focusing only on that one-dimensional motion perpendicular to the disk, we can compare the gravitational force that a star would feel due to the force pulling it back into the midplane, and essentially a pressure gradient which has to do with the velocity dispersion. So this is an equation you can derive from that collisionless Boltzmann equation, but it looks just like the equation of hydrostatic equilibrium that you might write down for an atmosphere. And so you take this equation, and that allows you to say something about the gravitational potential in terms of this velocity dispersion. You combine this with Poissons equation, which tells you how to relate the gravitational potential with the total density, not just the density of the stuff that you're using to trace the gravitational potential. And combining these two, that allows you to say something about the total mass density in the solar neighborhood. And this has come to be known as the Oort program or Oort problem. Measure the density and dispersion of tracers as a function of z, infer the vertical potential, this psi of z, the potential relative to the potential in the midplane, compute the total density from Poissons equation, subtract the density of known objects such as stars, gas, and dust. It's not as easy as it sounds. And then infer the local density of dark matter. So all of this was laid out in a truly seminal paper in 1932 by Jan Oort, one of, I think, the real heroes of galactic dynamics. Kind of a clunky title, though. The force exerted by the stellar system in the direction perpendicular to the galactic plane and some related problems. I don't know why the related problems had to be there. So short titles, Jan. But anyway, remarkably, in this paper, you find a third purpose of this effort was the derivation of an accurate value of the total amount of mass, including dark matter, corresponding to unit luminosity in the surroundings of the sun. This is 5 years before Zwicky's paper on dark matter in clusters of galaxies, and decades before Rubin and Ford. And he was already thinking, not about dark matter in the modern context, but how to use dynamics to find mass that you can't see or that's not readily visible. Interesting to go back to even earlier papers by Jeans and Kepten where some of these ideas were laid out. But Oort was really the first that had the correct model of the galaxy. So there's a long history now of attempts to use Oort's method to find the local dark matter density. This is a table that I'm certainly not going to go through here in a review by Justin Reed. And a compilation of these results, which is what do we say for the local density of dark matter. So you're plotting local density of dark matter on the vertical axis, surface density of the baryons, all the stars and the gas and the dust on the horizontal axis. Not surprisingly, they're anti-correlated since you're subtracting the baryons from the total to get the dark matter. And here's sort of a typical value that people who actually look for the stuff underground in underground detectors think about for the solar neighborhood. So all of this has assumed that the galaxy is in equilibrium, that we have a galaxy that's axisymmetric and symmetric about the midplane. But galaxies clearly are not equilibrium systems. You just have to look at all of these beautiful pictures of galaxies, see these prominent bars and spiral structure, and realize that these galaxies weren't born this way. They're probably not going to look like this 5 or 10 billion years from now. They're interacting with companions. They're certainly rotating. And so there's clearly dynamical evolution going on in these systems. This is this well-worn image from JPL that people use to describe what the Milky Way should look like. But the spiral structure of the Milky Way is still a matter of debate and discussion and a bit of a mess. And so here's, these are attempts to trace out the different spiral arms in the Milky Way galaxy. Galaxies also show departures from planarity. So here's this beautiful, well-known image of an edge-on galaxy, which shows what we call the integral sign warp. So you can see the idea of an integral shape here with the galaxy disk bending up on one side and down on the other. But galaxies show other types of behavior when looked edge-on that we're not seeing a perfect planar disk. The galaxies often have these undulations and warps in the outer parts. And here's a map from H1 observations of the Milky Way, showing that the Milky Way's galaxy itself is warped, rising on one side of the galaxy, below the plane on the other side of the galaxy, but with a lot of substructure in the warp. So there's complicated warping of the galaxy out of the midplane. So where does all this structure come from? Well, one idea is that the bars and the spiral structure and the warps can emerge from internal dynamics of disks. So we're very good at building equilibrium models of disks, but those equilibrium models can be unstable. And so if we simply take that equilibrium model I described early on in the talk, realize it as an n-body distribution, and simulate it using n-body methods, we find that the whole thing goes unstable. We form spiral structure, we form a bar, and the galaxy actually settles down into a different state than what we began with. So galaxies, we can construct axisymmetric equilibrium models, but for the most part, they tend to be unstable, and those instabilities may give us some idea as to how we form the structures that we see in real galaxies. Let's think a little bit about the nature of these instabilities. These instabilities are akin to something known as the Jeans instability, which is familiar to people who do cosmology. It's basically the idea that instabilities arise when gravity wins over pressure. And so if you think of a bit of material here with density rho, it feels a gravitational force toward the center, which I can write down here. This is really gravitational force per unit volume. And it's feeling an outward pressure, which is related to the gradient of the velocity dispersion. Putting these together, I find a radius that's the critical radius for collapse. If the radius is bigger than this, then gravity wins. If it's less than this, then pressure wins and the thing sort of expands. You could just as easily get this from dimensional analysis. but it's basically telling us that large objects collapse and small objects will just oscillate essentially as under pressure. So that's a very simplified view. What's happening with spiral structure in bars is more complicated. It involves what one of the giants in this field, Alar Toumre, called a conspiracy. It's a conspiracy of gravitational collapse, differential rotation, and this epicyclic motion that we talked about earlier. But the basic idea goes back to something akin to the gene's instability. So it turns out that bending of disks also can be generated just from the internal dynamics of the disk galaxies seeded by small amplitude perturbation. So you don't need to do anything to the disk to create warps. And this is something that Matt Checkers and I found in a series of simulations some years ago. So here I'm showing two simulations. We're looking at the surface density of two galaxies. The top row is a heavy galaxy that forms a bar. We've divided out that exponential function just to highlight what we're doing. And the bottom is a much lighter galaxy that doesn't form a bar at all, but forms a bit of spiral structure. So that's what's going on with surface density. Now let's look at the same two models, but this time in how much they're bending out of the plane of the galaxy. And so what we find is that we get this warping in the inner parts of the galaxy, which then migrates outward. And eventually we get fairly prominent warps in the outer parts of the galaxy in both of these models. And so just from the internal dynamics and the shot noise of the simulation, one can actually get warping of galaxies. And there was just a recent paper by Jerry Selwood and Victor de Battista kind of explaining some of the physics of this phenomena just about a month ago or so. As with spiral structure, the origin and evolution of warps remains an area of active research. Warps are somewhat complementary to the gene's instability. In this case, gravity is the thing that's providing the restoring force. The destabilizing force for a warp is thought to be the motion of stars as they move through a bend in the disk. So if you imagine taking a disk and bending it and having some stars moving through the bend, then the centrifugal force, centrifugal action, is going to try to cause that bend to move out a little bit, while gravity is going to try to restore the bending back to the plane. And so you can imagine that in some cases you get oscillations, and in other cases you get a more persistent bending in the disk. So that's the internal dynamics, but there's a lot more going on in galaxies that might cause these disruptions. So one is the satellites, like the large and small Magellanic Clouds that we talked about earlier. And so here's a simulation that my collaborators and I ran sort of many years ago, but I think it really nicely illustrates what's going on. We took a model of a galaxy that was stable against the formation of bars. We turned about 10% of the smooth dark halo into subhalos, and then we let it go and asked what effect do these subhalos have on the disk of the galaxy. And what we found is that you get much more prominent spiral structure as these subhalos, clumpiness in the dark halo or satellite galaxies, if you like, pass through the disk. And in fact, we form a bar in this particular galaxy, even though had we done this with a smooth halo, we wouldn't have found a bar. And let me jump ahead. Well, it's going to be there anyway. Let's see. We'll jump ahead just to the edge-on view, and you can see very nicely that all of this substructure is also launching waves in the vertical direction. And so this galaxy is doing just what you would expect it to do. We have the ripples in a pond effect. The galaxy is tilting because it's transferring angular momentum to the dark halo, and also getting some warping in the outer parts. So now I have to make a brief interlude to talk about astrometric observations. These were sort of the most obvious examples of disequilibrium. I'm going to talk about some more subtle examples of disequilibrium, and for that we need to talk about the Gaia Space Telescope, which is providing some phenomenal data for this field of galactic dynamics. So just a few slides on astrometric observations. Again, we're using a coordinate system in which r describes the distance from the galactic center Z, the position relative to the midplane, and an angle phi, which takes us around the galactic center. So in doing astrometric observations, our goal, our aim is to measure all 6 components of a star's position and velocity of its phase space coordinates. We want the distance to the star, its angular position on the sky, its motion on the sky, and its line of sight velocity. And so this is an old program dating back well before Tycho Brahe to Hipparchus back in ancient Greek times, and many other astronomers in other cultures. But Tycho Brahe, I think, was one of the early ones to really try to turn this into a science, measuring the angular positions of about 750 stars to arc-minute accuracy. So an arc-minute is about 1/30th of the full moon. We get the line of sight velocity to a star by using the Doppler effect, as you might imagine. So we take, one takes spectra of stars. Here's the calcium triplet in the spectrum of a star. The blue curve is some synthetic spectrum, some template, a library that you look up. And so you pick a spectra from this library, you Doppler shift it, and then you fit it to the spectra of a particular star. And that amount of Doppler shift then tells us what the radial velocity is. So this was something done by a number of different surveys. To get the distance, as we all learned in an elementary astronomy course, you can use parallax. That's the most concrete way of getting a distance to an object. You're measuring the shift in the position of a star relative to how it appears from distant stars due to the Earth's motion around the sun. So that's parallax. The problem with parallax is that for the closest stars, the parallax is only 1 arcsecond, which is about the resolution limit of most telescopes. To reach the galactic center, we require 10 to the minus 4 arcseconds, which is an extremely tiny angle, 1 over 10,000 over 3,600 of a degree. In addition, stars have their own motion perpendicular to the line of sight, which is dubbed proper motion. And I can't resist showing you this beautiful image of the Big Dipper over 200,000 years. The Gaia satellite is aiming to measure proper motions over 5 years. So think about that motion of these stars in the Big Dipper over 200,000 years, and then imagine trying to measure those positions, the shift in those positions on just a few years. So over a period of 5 years or so of this Gaia mission, what will a star's motion on the background sky look like? Well, it's going to look like these little curly-Q patterns. The circular motion is due to parallax effect of our motion around the sun, and then the drift is due to the proper motion of the star on the background. So this takes us to Gaia. The galactic field of galactic dynamics is really being propelled forward by data from the Gaia Space Telescope. It's a facility operated by the European Space Agency. The Gaia satellite was launched at the end of 2013, and it's now sitting out at the second Lagrange point. It aims to measure parallax and proper motions to an accuracy of 20 micro arcseconds over 5 years for 1 billion stars. And so that corresponds to a shift in the position of a star by about 1/5,000th of an arcsecond. And so here are these curly-Q patterns, and if you project them onto Mars, for example, where 1 arcsecond is 350 kilometers, that's an arcsecond, and now shrink by a factor of 1,000 or more. So that's what Gaia is doing. It's measuring distances that are corresponding to meters on Mars. It's just remarkable. This is a really nice plot from Michael Perriman, which describes how we've done in measuring positions and velocities of stars over the ages. So we go back from ancient Greek times to Hipparchus, the person, and Tycho Brahe, and then we have Tycho the survey and Hipparchus the survey now in the 21st century, which are measuring these positions and velocities with various accuracies for hundreds of thousands and millions of stars. And then Gaia makes this huge jump to 1,000 million stars, and a huge jump in accuracy. And what is also truly remarkable about Gaia is it's making all of this data available without any proprietary period. So what can Gaia see? Well, remember we had this image of a rotation curve. We have all these stars scattered in terms of their azimuthal velocity and radius. When one actually plots up the azimuthal velocities and radius for the stars in the solar neighborhood, you find these interesting ridges. And these ridges seem to follow lines of constant angular momentum, suggesting that there's some phase mixing going on. Something perturbed the disk, and then the stars diffused out over lines of R and V phi at constant LZ. And I think the origin of these is still something of a mystery. We talked about the VR V phi plane. This was the epicyclic motion. So this is what it looks like in one of those nice isothermal models that theorists invent. And here's what it looks like in the real distribution of stars from the second Gaia data release. Astronomers can't help themselves in trying to name things, so all these little clumps in this diagram get their own name. But there's a lot of physics here, and the thought is that these clumps have to do with stars trapped on orbits in resonance with the bar. So that's a whole talk in itself, trying to understand all of that structure. Finally, we come to bending waves, which were actually detected in the Sloan Digital Sky Survey. So it appears that the Milky Way not only has a prominent warp, but also undulations between the position of the sun and the outer part of the galaxy. And so maybe I'll, in the interest of time, just skip that. But the Milky Way not only is warped, but it also has these corrugations. So this takes me to something that my collaborators and I worked on beginning back in 2010. We had this idea of taking another run at the Oort problem using data from Segway, which is an offshoot of the Sloan Digital Sky Survey, where one has observations both above and below the galactic plane. So even though these are all in the northern hemisphere on Earth, they're measuring north and south of the galactic plane in galactic coordinates. We first made a plot of the number density of stars as a function of position relative to the galactic midplane in the solar neighborhood. So essentially projecting down out of all velocities and just plotting this number count. We found that it was nicely fit by a thin disk and a thick disk, which is something astronomers have known about for many years, that our disk of our galaxy has two different components. An inner thin disk and then a warmer, higher velocity dispersion thick disk. But what was at first an annoyance was the fact that when we took residuals of our model to this simple two-disk fit, we found these sort of 5 and 10% residuals that were asymmetric about the midplane of the galaxy and couldn't be removed by doing something simple like just saying our sun is at a different position relative to the midplane, and couldn't be explained by anything having to do with the Sloan selection function. We soon came to realize that this might be a new signal of disequilibrium in the solar neighborhood. One of the other things we did was look at not just the number of stars as a function of position from the midplane, but also the first moment of the vertical velocity. And here we also found something interesting. We found that the stars below the disk seem to be moving away from the midplane, and stars above the disk also seem to be moving a little bit away from the midplane. So there's, again, an asymmetry. The disk of the galaxy seems to be moving in and out and also bending up and down. And so there's complicated motions even in the velocity dispersion, which is the RMS velocity. So all of these things have been confirmed by other researchers with other data sets, such as the RAVE and LaMost surveys, and now Gaia, and seem to indicate that the solar neighborhood is a bit out of equilibrium, and something must have caused that. Well, let's jump ahead to the Gaia era. So here's this ZVZ plot that we talked about in an earlier slide. This is a nice equilibrium distribution that a theorist constructs on the computer. And this is what was found with the Gaia data by a group led by Antoja et al. Almost immediately after the Gaia data was released. And hopefully you can see that there's a little spiral that's coming out here. And I'm going to show you some sort of better examples of that. But you can just kind of get hints of a faint spiral pattern in this ZVZ phase space. So nothing to do with spiral structure. This is a spiral in the ZVZ phase space. So it seems that what this is the deprojection of the number count asymmetry and the velocity type asymmetries that were found in previous data sets. Rather than look at moments, look at the distribution itself, and that reveals a lot more physics. Indeed, it revealed this spiral, which was a surprise to almost everyone in the field. So what gives rise to this spiral? Well, if you take stars and give them a kick in the ZVZ plane, that is, you're giving a kick to the star, to the disk, and making it bend a little out of the midplane, if the potential were a perfect harmonic potential, then that kick would just cause this distribution to rotate around, because in a harmonic potential, everything has the same frequency of oscillation. But of course, the potential isn't harmonic. It's anharmonic because the density is decreasing as you're getting away from the midplane. And so when you put this kicked distribution in an anharmonic potential, you find spiral-type patterns, essentially because the stars close to the midplane are orbiting faster than the stars further away, where the density is lower and the potential, again, is deviating from the harmonic potential. So perhaps this is what we're seeing in the ZVZ plane. We're seeing the remnants of an early kick of the galaxy that displaced a bit of the disk and created this phase-space spiral. So there's some interesting open questions. For example, we can ask, is there a common origin to or dynamical connection between some of these different manifestations of disequilibrium? This is a simulation, an analysis of a simulation that Keir Darling did as part of his master's thesis, in which we look at the formation of spiral structure and warps. You would think that the dynamics of how those formed are actually decoupled from one another. Keir was able to apply something called dynamic mode decomposition, which seems to indicate that these different types of features in the disk may be dynamically coupled to each other. You could also ask if the corrugations in the disk and the local phase spirals are transient phenomena or from some recent event, and wonder about what's driving the departures from equilibrium. Is it internal dynamics, or is it an interaction with some outside agent like a satellite galaxy? And so we could go back to this idea that the disk is constantly being perturbed by these dark matter subhalos, and perhaps these are the things that are prompting the little phase spirals that we're seeing in the solar neighborhood. So this is maybe a bit of a busy plot. There's been an idea that the Sagittarius dwarf galaxy, which is actually one of the largest dwarf galaxies in the Milky Way, but only discovered fairly recently because it was hiding behind the galactic bulge, but recently passed through the disk of the Milky Way, is the thing that has prompted all of this structure that we're now seeing in the solar neighborhood. I guess the best way to describe the state of the art in this game is that one can get qualitatively good features similar to what we're seeing in the data, but it seems like there are features in the data in detail that can't be explained in the simulations, at least just yet. So it's an open question, and there were some recent interesting failures by a group at Toronto to try and explain all of these phenomena, and they seem to find that none of it really works. So there's something here that still requires an explanation. Finally, there's a question of whether self-gravity is important. Self-gravity is clearly important for bars and spiral structure. The question is whether it's also important for these phase spirals, or whether they can be understood just from kinematic phase mixing, like that little toy model that I showed earlier. And this is something, again, that Keir and I looked at. We just had a simple toy model of a 1D distribution. If these perturbations in the disk are driven by self-gravity, then you don't form phase spirals at all. You really need the particles to be very close to test particles in a background potential to get the nice phase spirals that are seen in the data. So this is further clues as to the dynamics of the galaxy. So let me, in the final few minutes, talk about this idea of revisiting the Oort problem that we talked about earlier. And this is something that Kevin Lee and I have looked at and are continuing to look at. The aim is to simultaneously infer the local gravitational potential and distribution function of a tracer population of stars using the second data release of Gaia. And a feature of this method is that the phase spirals will emerge as residuals of the model, and then in fact you can go back and use those to learn a bit more about the gravitational potential. Just to give you an idea of what one is up against in this sort of game, you can't just take all of the stars in the solar neighborhood. You have to look at the stars and think carefully about whether you have a complete sample of stars or whether you're limited by the fact that fainter stars that are further away aren't showing up in your survey. And so we picked stars in the giant part of the color magnitude diagram. We looked at the number counts and found the same asymmetry that's been seen throughout by Gaia now and Sloan and Lamoste. We modeled vertical potential by a simple 3-parameter model that dates back to some important work on the Oort problem by Koiken and Gilmore in the 1980s. It's a simple model that looks sort of harmonic near the midplane of the disk, which is what you would expect, and then becomes anharmonic as you go away from the midplane. So here's the model potential, and here's a harmonic extension of the potential in the inner part. So it's this anharmonic bit here that's going to give rise to the phase spirals. For the stellar distribution function, a single isothermal component is inadequate. As I already mentioned, the galaxy has a thick disk, what appears to be a thick disk and a thin disk. And this is something that, again, goes way back to the 1980s. But more recent work by Joe Bovey and collaborators has suggested that we really think not about a thin disk and a thick disk, but a whole sequence of stellar populations, each of which have their own vertical velocity dispersion, each of which is approximately isothermal. And they can be labeled not only by velocity dispersion, but also by their chemical composition, things like the alpha to iron ratio. And so you can think now about not just a 6-dimensional distribution function, but also a distribution that takes into account chemical abundances. So we propose to modify this exponential or Maxwellian type distribution and replace it by something more general. We call it the rational linear distribution function. I think Bernoulli df is better because this is kind of the Bernoulli formula for the fundamental constant E. In any case, this distribution function can actually be written as a superposition of isothermal subpopulations. So it seemed like a good candidate for the distribution function of stars in the midplane of the disk. So we went ahead and inferred the galactic potential, and I won't go in detail through this. We found that the potential we inferred was comparable to the potential found in the literature, with uncertainties that were also comparable to what was found in the literature. But probably the most important thing, the most interesting thing we found is that if we take the data, which is now for the first time data in the ZVZ plane, and we take our model, and we subtract them, then we find the beautiful phase spirals that Antoja and company found. And so we're now able to fit an equilibrium model to the data and look at the residuals and find these phase spirals. You can furthermore take these phase spirals and make a mapping not from the ZVZ plane, but from a plane that has to do with the vertical frequency, that oscillation frequency way back from the beginning of the talk, and an angle of the star in that vertical oscillation, angle action variables, for those of you who have done advanced dynamics recently. And then you find that these spirals map onto essentially diagonal bands in this omega theta space. And the slope then determines something like the time since whatever event created this spiral occurred. And so you read off the slope, and you would interpret that the event occurred something like 540 million years ago. So this seems like a nice program that then you can go back and say, well, does this make sense, or can we get further information about the galactic potential? We were then able to take our distribution function, decompose it into its constituents, and see if it fit with that Bovie data, and that's our blue curve, which seems to fit reasonably well through the red histogram. So it seems that that ad hoc rational linear distribution function is capturing something about the distribution of stars in terms of their vertical velocity dispersion. Well, the story doesn't quite end there. This is the faint spirals that Antoja found, but they also did something really clever and I think remarkable. They plotted the mean radial velocity. So instead of just plotting the number of stars as a function of z vz, they plotted the mean radial velocity and the mean azimuthal velocity, and then the spirals really pop out. So these stars are not just creating spirals in the z vz space, but they're doing something interesting in the r and phi directions, in the radial direction of the galaxy and the azimuthal direction. And so this leads us to our next project, and certainly what will be the heart of Kevin's PhD thesis, which is to extend our method to the full 6-dimensional phase space, which now includes all 3 types of oscillations and 3 types of angles. If the deep projection from this north-south asymmetry and velocities led to these beautiful spirals found by Antoja, then it's up to us and others to figure out what the deep projection now to the full 6T phase space leads to. So here's my summary of where we are in the game of galactic dynamics. We have all of these different observations of galactic disequilibrium. So these ridges that we're finding in the rotation curve, the clumps in the VR v phi space, the warping of the disk, the corrugations, the phase spirals, the north-south asymmetry number counts. I think there are good ideas about how each of these has formed, but to date, no one's really put it all together into a clear, coherent picture. But it seems that the prospects for rapid progress are good. Gaia is going to provide full phase space measurements for about 100 times more stars than are available at present. So it's not often you get 2 orders of magnitude increase in just a few years in an entire subfield of astrophysics, but that's where we are. And it will take a major effort that combines theory, simulations, and data science to piece together a complete and coherent picture of the dynamical state of the galaxy. Thanks.
Awesome. Thank you so much, Larry. And for those who are tuning in on the live stream, just as a reminder, you can post a question to the shared document, and we will ask that question out loud. But for now, we'll go to the people who are in the room. Do we have any questions to start?
Thanks, Larry. Does the fact that these are stars burning hydrogen and heating up and occasionally having big supernovas that could explode and cause weird things going on, does that ever change any of this large-scale galactic scale dynamics?
So the dynamics of the stellar component, I would say no. So certainly the star formation processes are affecting the gas components of the galaxy. I'd say to sort of turn your question around a little bit differently, there's an entire field, subfield of this subfield called chemodynamics, in which people are looking at chemical abundances of stars. They're trying to figure out where the stars were born in the Milky Way and how that what the interplay between that and the dynamics is. And so can we trace together the star formation history of the Milky Way? Did the stars, form the inside out, or, where did the stars form first in the disk, and how was the disk assembled? And all of that is in not just the kinematic data that I've been showing, but all of the chemical, and spectra that Gaia is taking as well. So, that six-dimensional phase space is just a fraction of what Gaia is doing, and companion surveys. So.
Hi, Larry. Thanks for the cool talk. I wonder, in dark matter, we ask about if there's clumpy dark matter, some sort of like power spectrum or certain size of clumps. With all this fine, detailed data, are you able to make any statements about?
Right. So a way to rephrase your question is, are we going to learn something about the agent that perturbed the disk, or are we going to learn something about the dynamics of the disk? So, will we learn, if we really start to map out phase spirals, corrugations, and all of this substructure, is that going to tell us something about, the mass spectrum of substructure that's constantly perturbing the disk? Or is the disk in such a state of continual perturbations that really what we're learning about are kind of the normal modes of the disk that's just being perturbed by everything? So I see those as kind of flip side of the same, exactly the question you're asking. But yeah, we don't know how much, we know how much visible structure there is in the Milky Way. We know that there are like 40 or 50 or so satellites. And we know, roughly their mass spectrum. We don't know anything about the clumpiness in the dark halo, apart from the stuff that's surrounding the satellites themselves. So, yeah, and there's all bunch of stuff that's going on with halo substructure and other areas of cosmology, as you know.
Yes, I had a hopefully not too technical question. If I want to go and use, say, the Jeans equation to solve for the velocity dispersion in some system, and I don't know what the actual physical distribution, spatial distribution is, that assumption, say thin, thick disk, or whatever it is going to go and give me a different, or a specific velocity dispersion as a function of radius. And so I'm wondering how important those assumptions are. So they seem to be fairly important towards the end, but what I'm really wondering is whether there's still a place in that assumption of the spatial distribution of your stars for an equilibrium distribution to be hiding. And the reason we think it's out of equilibrium, or the reason some of these phase-space structures are there, is just that we had the wrong ansatz when we were solving our Jeans equations.
So we're seeing these structures just in projections of phase space, right? And so there's no sort of interpretation in the ZVZ plane. That is what we're seeing there. It's hard to imagine how that could be sort of an artifact. I'm not sure where the wrong assumptions would be, but I think I see what you're saying. So there's the underlying gravitational field, which comes from the total mass, but then there's the density of tracer populations, which then you use in the Jeans equation to...
Like, could I come up with some equilibrium solution that has spiral structures in the
these little phase spirals?
Yeah.
I think that would be hard. That would be hard to construct, just because, that phase space is always rotating, and unless we know the potential isn't a harmonic potential. In that case, it would just be a solid body rotation, but. So we know that much. So the fact that we see these spirals is already telling us, I think, that something
happened.
happened.
It's not the simplest assumption.
Yeah, I don't think it's a big leap to say that this had to be, if it's real, then it had to be some out of equilibrium thing. Whether it's as simple as just phase mixing or something more complicated, I think, it's an open question.
Any other questions? All right, I'm going to ask one. Regarding these oscillatory behaviors that happen in galactic disks,
Yeah.
do we have to worry about them being powerful enough to eject material from the galaxy, and this could be a source of material going into the intergalactic medium, and that could, further potentially affect your, galaxy model and your potential distribution?
Well, there's a term that's come up in some of these discussions called the kicked up disk. And the idea is that you can, perhaps some of these perturbations are actually able to take stars and perturb them so much that they're no longer in these approximate circular orbits. They're basically in orbits that look like stellar halo orbits, but they're disk stars.
So they're still bound.
So they're still bound to the galaxy, but you would identify them kinematically as stars in the stellar halo. But then you look at their chemical abundance, you look at other properties of the stars, and you realize, wait a minute, these look like disk stars. And so the hypothesis is that these are stars that were in the disk, probably in the outer part of the disk. Something came through and kicked them into orbits that could no longer be described as a disk orbit. And so that's been an active game, and I've even been involved in some of that as well. So.
Excellent, thank you. All right, well, we're past the half hour, so if you have additional questions, I'm fairly certain everyone in this room knows how to find Larry, but thank you very much. Let's thank him again for a wonderful colloquium.